In the last video we looked at carbon diamond and carbon graphite, both giant molecular substances. And in this video we're going to look at fullerenes and graphene. Now the thing they all have in common is they're all made of carbon atoms. Graphite and diamond, as I said, are giant molecular structures, and now we've got these two here, also made of carbon. So this one here is fullerene, sometimes called Buckminsterfullerene, and it's made totally of carbon atoms. Okay, so what it asks us to do here is to look at the structure of Buckminsterfullerene and then state what type of structure it is, i.e. ionic, simple molecular or giant molecular. So the first thing to say is this is made of carbon, okay, carbon. These are carbon atoms. And carbon atoms are non-metals. So that immediately rules out ionic, because an ionic bond is between a metal and a non-metal, so it's not ionic. So the next question, is it a simple molecule or is it a giant molecule? Now, this is a regularly asked question by the Edexcel examiners. And everybody looks at this and say, oh, that's quite a big molecule. It's shaped like a football. Actually, if we look at it carefully and look at some footballs and how they're made, the pentagonal and hexagonal rings interlocking, it looks just like a football, sometimes called the buckyball, this molecule. Anyway, students look at it and say, it's quite big. It must be a giant molecule. And of course, they are completely and utterly wrong. Okay, this is a simple molecule because all these covalent bonds, because each of these grey lines here in this molly-mud, between these black carbon atoms, each of these covalent bonds connect to another carbon atom within the molecule. There are no covalent bonds coming out of the molecule to other carbon atoms and other molecules. So this molecule is self-contained. Okay, all the bonds start and finish within that molecule. It is a simple molecule. Okay, simple molecule because the bonds start and finish within that molecule. If we think about diamond, the bonds keep going on forever and ever and ever. Each carbon atom bonds to 4 other carbon atoms, and those 4 carbon atoms bond to 4 other carbon atoms, and that just goes on forever and ever. This circles back in on itself. So that is a simple molecule. Okay, very important. So that's another form of carbon. So we've done diamond, graphite, and that is fullerene, Buckminsterfullerene. Okay, so the next one, so we've got, we had to do the structuring explanation, didn't we? So that was simple molecules for Buckminsterfullerene. Okay, the bonds, the covalent bonds, start and finish within the molecule. Okay, so graphene is the next one. Sounds a bit like graphite, doesn't it? And it is. It's very similar. Graphene has an identical structure to graphite, the only difference being it's just 1 layer thick. So in the video the other day, if I've still got it to hand, when we did graphite, we had this layer of graphite here, and then we had delocalized electrons, and another layer of graphite, then delocalized electrons, then another layer of graphite. And those layers of graphite build up, and there's billions of them in a pencil lead, a pencil graphite. The graphite is in the end there, and it goes all the way up the pencil. And there's literally billions of those layers, and every time we scrape the pencil over a piece of paper, we scrape a layer off, and that's what the pencil mark is that's left behind. It's a layer of graphite. Now graphene is exactly the same as one of these layers of graphite, okay, but just one. That makes it tremendously thin. And it asks us to draw that, so we can simply draw 1 layer of graphite. Now remember, in graphite, carbon only forms 3 bonds. So we have these hexagonal rings. Okay, they go on forever and ever. This is a giant molecular structure because this goes on forever and ever. It doesn't circle back on itself like fullerene. And it's forming 3 bonds, 1, 2, 3. Now remember, carbon wants to form 4 bonds. So there is that delocalized electron still that sits beneath the layer. Okay, structure of graphene, giant molecular. Okay, now we need to be able to explain the properties of these things for fullerenes and graphene on the basis for their structures. Okay, so we've got this little table down here. Structure, we've said already, Buckminsterfullerene, simple molecular. Graphene, giant molecular. Melting point of this one is going to be low because it's a simple molecule. Melting point of graphene is going to be high because it's a giant molecule. Right, electrical conductivity. Okay, now this was an exact question in the, I think it was the 2018 EdXL paper 1 about, and it discussed about fullerenes and, was it fullerenes that came into that? But certainly graphene did. Anyway, electrical conductivity. Carbon here in the fullerene forms 1, 2, 3 bonds. Carbon wants to form 4 bonds, if you remember back to the giant molecular work we did on diamond and graphite. So this does have a delocalized electron that sits within this structure. So that will conduct. But remember, you've got one molecule here, it's a simple molecule. The next molecule might be over here, and the next molecule might be over here. How do the electrons get between the molecules? There's nothing to carry them. Okay, remember, a current of electricity is a flow of charge, either electrons or ions. In this case, it will be electrons. So the electrons can flow across the molecules, no problem with that. But how to get between molecules? Okay, so the electrical conductivity of Buckminsterfullerene is known as a semiconductor. Semiconductor. You might have heard of semiconductors, and more often than not, the silicon is semiconductor used in electronics and computers and things like that. Okay, so very useful, and that's certainly a use of Buckminsterfullerene. Electrical conductivity of graphene. Well, yeah, it's got its large sheets. They go on forever and ever. Delocalized electrons. Electrical conductivity, good. Okay, because those delocalized electrons can move. Uses. We don't really need to worry about uses for the EdXL course. I think they're still developing uses for Buckminsterfullerene, certainly as a semiconductor. I think they're looking at using it in medicine as well, seeing they're deciding they can put, I think, elements inside this Buckminsterfullerene and transport them around places, and that affects the conductivity as well and whatever else. But we don't need to worry too much about that, so let's not worry about that one. This is, of course, graphene. Because of the structure, giant molecule, it's extremely thin, very thin. And given its thinness, it's very strong. Okay, it's also a great conductor of electricity, so it's got tremendous uses in conductivity where we need something that's very thin, very light. Also, sporting goods seem to be picking up graphene. I've got my daughter's tennis racket here. See if I can just get that into the camera shot here. And what do we see? It says in the frame here, it's upside down, but it says graphene. And if you notice, you can just see some hexagonal rings built into the frame there. It is, of course, a complete marketing ploy. Okay, graphene, very strong, very light. Okay, there may be some graphene in that tennis racket. I imagine there is somewhere, otherwise they wouldn't be able to put graphene on it. But of course, they've been making carbon fibre tennis rackets for years without graphene. Not just tennis rackets. We've got my wife's skis here as well. And of course, we've got graphene also written on here. And you can see the hexagonal structures. They've built them even into the transfer on the skis there. The structure of graphene. Graphene, is of course mightily tiny. That's just a transfer on the outside. Again, it's just a marketing ploy. They've been making skis for years. But as a marketing ploy goes, it seems to be reasonably successful in our house, doesn't it? Because we've bought loads of stuff with it. So the use is around it being very thin and very strong, and that's what we need to know. We don't need to. I don't think we need to name a use, but if we do, you've seen a tennis racket and skis, sporting goods, things like that, where we want them to be light and strong. Okay, because that's the important thing. Very thin, very strong for graphene.